My name is Colin Fitzner, and I'm entering my senior year at the University of Michigan studying mechanical engineering. This summer, I participated in the College of Engineering's Summer Undergraduate Research in Engineering, or SURE program. I worked with Professor Bogdan Eperanu in the ME department on the modeling and identification of mistuning in bladed discs. The title of this topic is fairly technical, so some background information is required. Turbomachinery rotors, such as those used in newer jet engines, typically feature integrally bladed discs, such as this one shown. They are also known as blisks. Note how the blade and the disc are made out of one piece of material. This makes blisks very expensive to manufacture. Ideally, blisks are tuned, meaning they are cyclically symmetric, which allows us to analyze the entire blisk using a sector of the blisk. However, in reality, blisks are never perfectly tuned due to variations in the material properties within the blisk and due to manufacturing tolerances. These variations are called mistunings and can lead to deviations in the natural frequency from the tuned model. Deviations in natural frequency, in turn, create regions of high stress and energy which lead to high cycle fatigue. The mistuning destroys the cyclic symmetry, and we once again need to use a full wheel model in order to use finite element analysis. Note the different colors on the blades. These represent different stiffnesses between the blades. Instead of using a full wheel model, we can use a reduced order model to analyze the difference in frequency. The reduced order model uses a tuned sector finite element model and force response data from an actual blisk. This method is much cheaper than using a full wheel finite element model because it is faster, and a finite element model of the full wheel is not required for each individual blisk. Inside the reduced order model, we make use of Newton's second law in matrix form, where M is the mass matrix, K is the stiffness matrix, and X are the degrees of freedom. After manipulation, we arrive at this equation. The blue highlighted terms are terms that are given from the force response data. The green terms are terms that are given from the the sector model. The boxed red terms are terms we are trying to solve for. In particular, the second term, which is the change in natural frequency between tuned projection mode and the projection mode of a mistuned blade, is what I focused on. A mode is essentially the way the blade vibrates. Here are some of my results. The blue line shows the results of the reduced order model, and the red line shows the actual frequencies of each blade as predicted by the full wheel finite element model. As you can see, the results are accurate to within 0.1%. The bottom graph shows the frequency of the entire blisk for a variety of modes. The circles represent the change in frequency between the mistuned blisk and the tuned blisk. Thank you for your time, and go blue.